across my capacitor.
Goes high.
Yeah, it starts out very high. And then it's going to go down low. And then if I'm looking at my inductor, on my frequency response curve on my inductor, what happens is my voltage doesn't start out very low or very high. So where's my voltage at a very low frequency? Where's my voltage across my inductor?
Low.
Very low. It's just going to be just the opposite of the capacitor. That one's going to go across there. So those two are kind of going to react just the opposite. They're not really going to fight each other. They're going to actually aid in each other right at this spot here. This is the little primo spot here. This is where DC and DL are going to equal, X of L and X of C are going to equal, and those two are going to work together. And as the inductor is inducing a voltage in our circuit, the capacitor is going to bring in that energy. And when my sine wave starts to drop, that capacitor is going to put the power back into the circuit. And so they end up, actually what they end up doing then is they kind of sit there and they cancel each other out. And this is what we call our resonating frequency. This is right where X of L and X of C are going to equal. So the first thing that we want to do then is just go ahead and find out what is our resonating frequency for our particular circuit. And to calculate out your resonating frequency, which is this one right here, is equal to 1 over 2 pi the square root of L times C. And that will equal your resonating frequency. So what I do is when I'm doing this, is I go ahead and I take my inductance and my capacitance, multiply those two together, do the square root of those, multiply it by pi, multiply it by 2, and then hit my inverse key. And then that'll give me my resonating frequency on that.
The square root, is it CC or is it BC?
LC. Yep, so let's first find out what our resonating frequency at. What is this? At what point does this happen? Calculate out what your resonating frequency would be at that point. Yeah. So make sure you hit your equal sign or put these in parentheses before you do your square root. So make sure you do L times C and then your square root. Yep. Come up with. All right. So what do we get for resonating frequency?
734.4 microliters.
0.1 kilohertz.
What?
Did you get to the third? I didn't notice that. I just seen the number.
-6.
Yeah, -6.
I don't know what it did.
I don't think it did there either. Yeah, so actually I got 734.1.
Oh.
Yeah, you were close. I didn't look at what your. Yeah, so that's going to be your resonating frequency. That's where this circuit is going to actually work at its best performance there.
So would the angle be 45 degrees?
No, but we'll calculate that out, and then we'll see what we get. All right. keep that thought, but we're gonna take a look at that. So we're gonna kind of list everything again. What happens at our resonating frequency once we go through everything. All right. So now once we have our frequency, we know we're gonna set up our. This circuit here is gonna be tuned to filter out all the frequencies except for the 734.1 kilohertz. That's the frequency that's going to be coming out of our output. All right, so once we got that frequency, then what we can do is we can calculate out what our X of C is and our X of L is. Because now that we know our frequency, now we can go ahead and calculate out X of C and X of L. And what that would do is get in the habit of using your memory too. So once you got that resonating frequency, you know, if you're using the 30 X2 here, you know, hit your stow key and then either hit 1, 2, or 3 and put that into your memory location. If you don't know how to use your memory location, let me know and I'll show you how to use your memory location. But you should start storing those large numbers into your memory location. Yeah, so yeah, you got the same, yeah, so you got that 700, once you get that 734.1 kilohertz, yep, then hit stow, then press 1, that'll be your memory. Then you just hit, then you hit your recall button and then bring up that number 1. All right, so what do we end up for X of C? Okay, so you got 4.613 kiloohms. Okay, and then what do you get for X of L?
Same thing.
Same thing. We said that right here, that X of L and X of C are going to equal. So we know that my resonating frequency then, X of L is going to equal X of C. So then we should get the same thing. 4.613.
Which one are we working on?
Okay? So we're just taking so we just can calculate out our passive reactance just using our 2 times pi times our frequency of 734.1 kilohertz times our capacitance. Do the inverse of that and you should get 4,613 kiloohms. And then once you know that one, and since we know that we're at a resonating frequency, we know automatically that X of L is going to equal the same thing. All right. So now we got our X of C and we got our X of L. Now what we want to do is, we're going to stay with that. We can go ahead and we can calculate out what our X of T is. Okay? And our X of T is just equal to my, if I just add these two up together, add X of L plus X of C, so when I say that, we got to look at our vectors. Remember that X of L is going to be at our plus Y, X of C is at our negative Y, and then our X is going to be at plus X. So when I'm adding these things up using my vectors, I can just add the two numbers together. So X of C is going to be, I'm going to have a negative X of C plus my positive X of L. Okay, so when we're doing them in the vectors, even though resistance doesn't have polarity, but when we're doing it in the vectors, it does. So we can just take the sum of the two and get our X of T. So for example, we would have a negative 4,613 kiloohms plus 4,613 kiloohms for my X of L. And if I add those two together, I'm going to get what for X of T?
0.
0. So those two are going to cancel each other out, and I'm going to end up with 0 ohms. Okay? So I just add them up vectorally. Alright, so now we kind of took care of all our inductive reactance and our capacitive reactance. Now we can go to our resistance. Now we have a resistor in here of 220 ohms, and we also have some resistance in our windings of our inductor that we have to include on there. And that resistance of the winding, it doesn't matter where I have these resistance in a series circuit, it doesn't matter where any of this resistance is. I can just go ahead and add them all up. So whether it's inside the inductor or somewhere on that circuit, I just go ahead and I calculate out my total resistance. I just add them all. I just add up all my total resistance. Just I do like if I was doing a series circuit, I'm just going to do R1 plus R2 and so on, and that'll give me my total resistance. So what do I get for total resistance then? So what would be my total resistance of the circuit, including the resistance of the windings? It's just really basic. I mean, it's just as obvious as it is. 224. Yeah, about it. Yeah, that's as obvious as it is, right there. So you just take your total resistance and you put down 224. So now if I'm looking at my vector and I start putting it in here, my total capacitive reactance is 0. So that's going to be right here. This is where my X of T is. My total resistance of my circuit is going to be, somewhere approximately, we'll just say approximately right here. And that's going to be at 224 ohms. Okay? So now once I have my X and I have my Y, I can go ahead and I can do all my other calculations. But since I know that my X of T is at 0, and if I want to find the total impedance of my circuit here, my ZT, but here's my ZT, it's a vector. It's going to be somewhere between X of L and X of C. So where is it in this particular case? If X of T is 0, and my resistance is 224 ohms, my Z is going to be right here, right? So my Z is going to be the same length as what?
224 ohms.
224 ohms. Okay, so another thing that when we're at resonating frequency, Z is going to equal R. So Z, my total impedance of my circuit is going to be 224 ohms. Okay? Because right at this point, X of L and X of T are going to, or X of L and X of C are going to cancel each other out, and I have no inductance. I don't have any reactance in my circuit. Those two are just kind of canceling each other out. And so then it makes it a purely resistant circuit. Those two are just kind of ignored. The total capacitive reactance between these two is a 0 ohms. It's just basically just like a short when I'm going across both of them. So it looks just like a short. So the only thing I have left in my circuit is the resistance of my resistor and then a little bit of my resistance of my windings. Okay, so that takes care of all of our impedance then. Okay, so that all makes sense so far? Okay.
Your Z.
And believe me, I'm making this a lot more difficult than what it really is. It's just a matter of just taking it's everything we've done so far. The only difference is that we had to just subtract these two, and then that's our new X.
So X of T is always going to be 0. at residence.
What's that?
SFC is always going to be at 0 at residence.
Yes. Yep. So let's continue on with our phase angle then. We know that my Z is here. So what's my phasor angle going to be? We know that this is going to be a negative 90. This is a positive 90. What is it right at this point? 0. So then that's another thing then, is that we know that my theta is always going to be equal to 0 degrees. At my resonating frequency. Those are all the things that are going to happen at my resonating frequency. All right, so now let's figure out some of our other voltages that we got going across here. So a couple of things that we can do is that we can go ahead, we got enough information that we can go ahead and use Ohm's law, or we also can do our rectangular to polar function. Either one. But let's just kind of stick with what we know. We know that what remains constant in a series circuit? Current. So that would be the next thing I would do. I would go ahead and take care of my current, because I know once I figure out the current, then I have my current going through the whole circuit. So figure out what your current is going through the circuit.
$446.4 microamps.
Say it one more time.
446.4 microamps.
So 446.4 microamps. Everyone agree with that?
Yes.
All right, good. Okay, so then what we can do is we can just fill that in all over the place then. So we're going to put in 446.4 microamps here. 446.4 microamps here. And we also want to make sure that we keep the same units, so make sure we have our amps AC, so we know that it's already in an RMS value. All right. So now we got our current in everywhere. We can just go ahead and we can still apply Ohm's law then, and let's figure out what our voltage is across our capacitor, our inductor, and our resistor.
What the heck? Capacitor is 2.059.
Okay, say it again one more time.
2.059.
Then what's our units?
Volts AC.
Volts AC, good. Okay, and so then, again, we only have to calculate on one because I said at that resonating frequency, our voltage across our inductor and voltage across our capacitor are going to equal, right? And so we got 2.059 volts AC across there. So, and what do we have for our source going in? What's our voltage source?
100 millivolts AC.
100 millivolts. So did everyone get 2.059 volts? That is correct. That's exactly what's going to happen. Because remember, we were talking about when you light up your neon light bulb, when you collapse the magnetic field across that inductor, that light flash took about 120 volts, or well, around 80 to 120 volts to light up that neon light bulb. So what happened was that when that inductor started collapsing, it induced a large amount of voltage. Then that capacitor absorbed that voltage and stored that energy. So it does indeed end up equaling over 2 volts, even with just 100 millivolts circuit in there. Because whatever this energy is being stored in here, or whatever this produces, the capacitor is going to store. Then when my sine wave starts to decrease, that capacitor is going to put that energy back into that circuit, and it's going to charge up that inductor back up to 2.59. It's going to see that full source voltage going across that, and keep on repeating. So yes, we do indeed get almost over 2 volts of voltage going across our capacitor and inductor.
If you were to hook that up to a square wave and have a high frequency, would that have looked like it was lit up?
What's that?
That circuit with the neon light bulb?
We tried it with hooking it up to the square wave, but the circuit didn't quite work out. But yeah, you could, because that's exactly how a spark plug works. But that's a little bit different. That's a little bit different setup. But yes, we could though. We could wire it up the correct way so that you could do that, so that you did hook up the square wave. Because it's just like turning on and off the switch.
Well, I did, but I'm just curious.
But you need 2 separate coils. Yeah. But when you're in lab, we could give that a try. Show you that. All right. So then, what's my voltage across my? What's the voltage across my resistor?
98.21 millivolts AC.
98.21
2, 1.
millivolts AC. Okay. So that's almost. So when I said we were right here, those 2 voltages, those are going to cancel out each other. You know, and again, we can use this as either voltage or impedance. It doesn't really matter. But my total source voltage then is always going to ride approximately the same place as it does on my impedance angle. It's going to be right here. So my source voltage is always going to equal my VR. So in an ideal circuit, my voltage across my resistor, after these 2 get canceled out, should it end up equaling to my source voltage, but it doesn't. Why is that? Do you know anywhere where the other 2 millivolts goes?
It's the wasted power.
Yeah, whoever said that. Resistance, yeah. It's the remainder dropped across that resistance of the windings in here. So I got approximately 2 millivolts that are being dropped across that inductor. Okay? We can't really measure it. We can't see it because if we put a voltmeter across there, we're going to see the voltage across the inductor, not the resistance of the inductor. But that extra voltage ends up dropping across that resistance of the winding internally inside that resistance of the winding of the inductor. So that's where those other 2 millivolts goes to. And that can affect our quality of our circuit. We'll take a look at that when we start looking at our more of our graphs there. All right, so now we have all our voltages, and so here I am. I'm putting in 100 millivolts AC. This is my, a lot of times this is what our filter circuit looks like. They don't even show you the source voltage or anything like that. They just assume this is where my VN is, so it's just basically having me hook up my function generator up to it, just like this. I put in 100 millivolts AC into the circuit, and my V out then is going to equal 98.21 millivolts AC. And that's only going to happen when I'm at my resonating frequency at 734.1 kilohertz. That's when my V out is going to equal approximately to my source voltage. All right, so then let's finish up the rest of this, and then we'll take a look at our frequency response curve of the circuit here. Well, one thing here, let's take a look at. Let's stay with our voltage here for 1 minute here. So we know that my voltage across my capacitor is going to be at 2.59 volts AC. My voltage across my inductor is going to be 2.059 volts AC. So if I put an oscilloscope on there, I would see that. I would see that voltage. if I put my oscilloscope across the inductor, I would see that voltage. I'd see that RMS voltage. If I were to put my oscilloscope across both of them, assuming it is just for the voltage meter, if I put my voltage meter across both of them, what I end up reading is 0 volts. Never read 0 volts, because if I do my little phase shifts on here, I know that my VL is here, my DC is here, and then my VR is here. So my VR is going to still be at 0 degrees. My voltage of my capacitor is going to be where? In relationship to VR, where's my voltage of my capacitor? Is it leading or lagging VR? So here's my voltage of my capacitor. So here's my voltage of my resistor. This is at 0 degrees. This is at negative 90 degrees. So where's my voltage of my capacitor in relationship to VR?
Leads.
If this is at 0 degrees, and this is at negative 90 degrees, it's going to lag by 90. Because it's 90 degrees behind VR. So my voltage of my capacitor is right here. And then my voltage of my inductor is going to be where? Is that going to be leading or lagging VR? And that's going to be leading, and that's going to be leading by how much?
90.
By 90. So here's my voltage of my inductor here, and I'm going to see if I can draw this correctly the right time first time here. It is first time. So here's VL. So if I'm looking at that, I know that you can see that my voltage of my inductor and my voltage of my capacitor are exactly 180 degrees apart. So if I'm looking at, if I'm measuring, if I take the, if I have one that got, I got a voltage of across the capacitor that's at 2.059 volts AC, and that's in the positive voltage at that time, and then I got my inductor is actually series opposing that voltage, and that's going negative at that time. So those two are going to cancel each other out, and that's where I end up getting 0 volts because of the phase angles of each one of these. Because VC is going up when VL is going down, and they're opposing each other's voltage, and the capacitor is opposing the voltage of the inductor, and the inductor is opposing the current of the capacitor. And those two are going to cancel each other out. They're going to oppose each other. Because this one here is going to be, at one half of the cycle, I'm going to be positive, negative, and this one's going to be negative, positive. And so those two are going to be always opposing each other. But they're going to be taking all the energy that the inductor produces, the capacitor is going to store it, then the capacitor is going to discharge and put it back into the inductor, and the inductor is going to oppose that change in current. So that's where we get that 0 volts going across it. But if I do separately, measure them across separately, I will measure that 2.059 separately, but going across both of them, then they cancel each other out because of the polarities of them. And that's why we can just go ahead and take our V total is the same thing right here. Here's our V total. We just kind of cancel those things out. We can just go ahead and add them, algebraically add them together, take my DC plus VL, will get me my voltage total of 0 volts. Or my source voltage, I'm sorry, of 100 millivolts. Or, no, my voltage, I should say my, how do I want to say that? My voltage of my passive reactance total would be 0 volts. not my source voltage. So we put that one right on the 0 there. So my VS is going to be somewhere in between here, but if I cancel those two out, it's going to be sitting right on top of VR. All right, so let's. So any questions so far? Is that starting to make a little bit of sense there? Okay. All right, so let's take a look. Let's just finish this all up. So now we can just go ahead and let's just calculate out our powers. I made it easy on you because I made it as an AC voltage. But remember, if this isn't a peak-to-peak voltage or a peak voltage, you'd have to first convert this into an RMS value before you can calculate out your powers. Okay? So be careful of that. Especially on the final, make sure you look. Make sure that it's already an RMS value before you calculate out your power. Power is never calculated out using our peak voltage or our peak-to-peak voltage. So let's calculate out our powers here real quick.
Question for you.
Yeah.
If in the exam you have your V source as peak to peak,
Yep.
do you want your VR and your
Everything should be in
VXL all peak to peak, or do you
Yep.
want them all RMS?
Nope, keep them peak to peak.
Okay.
Yep, whatever your given value is, stay with that other than for the power.
Okay.
Yep, always stick with that same. Yep, because there's a lot of times there's a reason for it. Because typically all your test points and everything that they give you, then is always going to be in that same unit.
Okay.
Yeah. But if you're calculating out power, just know that it's going to be an RMS value. And typically, most cases, depending on what our signals are, well, like if we're doing radio signals or anything like that, because like if I'm going to broadcast, a radio station, I'm trying to output a bunch of power, right? So we already know that that's always going to be an RMS value because it's power. It always has to be related to the power. So we always make things easy on us, so we're going to always stick with the RMS value. So like on audio circuits and stuff, a lot of times they are already RMS values, especially on the output stages. Yep. Because that's the power coming out of our antenna, and that power has to be calculated out using an RMS value. But if we're doing just basic signals, then it could either be a peak or peak to peak. All right, so what do we get for power of our capacitor then?
19.1 micro.
Can you tell one more time, Isaac?
919.1 micro.
$919.1.
Micro.
And what's our units for reactive component?
VR.
And that's going to be, I screwed that up to begin with, but it's actually VAR.
VR.
Yeah, volt amps reactance. At the beginning of AC, I screwed that up. Yep, so we'll just correct ourselves now. Okay, then once we know that the power of our capacitor, what's going to be the power of our inductor then? It's going to be the same. Microbars, volt amps reactance. And then what's my power of my resistor?
43.84 microwatts.
Can you say it one more time?
43.84 microwatts.
43.84 microwatts. Good. Okay, and then my total power,
44.64 micro.
and that one's going to be just our VA. It's a combination of our volt amps reactance and our true power. Yeah, and it should equal up to, because now we do have a little bit of loss in our power, but ideally, if this is an ideal inductor, our power total would equal just the power of our resistor. So in an ideal inductor, then this PT and PR would equal. But since we do have a little bit of the true power being lost across here, that's where that rest of that remainder amount of power is going. And that's going across that inductor. And that would be what would cause that inductor to heat up. That's the only thing that would cause that inductor to heat up is that resistance of that winding. That would be our true power going across that inductance of the winding. Otherwise, this here power, remember, is just apparent power. There's no, it's not producing any heat, light, or any other type of energy. It's just our apparent power. But since we do have a little bit of resistance across there, and we do have a little bit of power being dropped across it, that inductor will heat up just slightly, depending on the size of it. All right, okay. All right, so any questions up to this point? All right, well, before we go into the rest of it and start getting into our frequency response curve, why don't we take a 10-minute break and then we'll come back and we'll finish up our circuit here.
Like my test.
I love it. And you're exactly a half hour late, too. I told you you'd be here by half hour.
Oh, yeah.
Say RMS or
No, I woke
PT?
up at 7 o'clock.
Considered RMS and
You know, I love my.
Well, remember, RMS and AC is one and the same. So if I talk about an outlet here, you know, if I say 120 volts AC,
I cannot
Yeah,
get out of the house in less than a half
that's
an hour.
another good example. You know that, because I could really say that I have,
It's so difficult.
I think it was, it comes up to
Oh,
you.
they
I could
make-
say that I have 339 volts peak to peak coming on my outlet, but we always use RMS because you ever look at everything, all your light bulbs are considered in wattage, your toasters, you know, wattage, you know, hair dryers, everything's based off of the wattage, so that's why we keep that one as an RMS value.
Gotcha.
Yeah. Yeah.